So what will happen again after this, after a short delay here, right, which is the PCQ delay of the flip-flop, this will come out and it will read subtraction, right. ALU control E is just a signal, is just ALU control D delayed by 1 clock cycle, right, and therefore you have the subtract signal happening here. Likewise, the RDE, right, is going to be again a delayed version of RDD, and therefore that will again happen after TPCQ, right, and this is going to be S2, right. Now my result E, right, question is what happens to this signal? What is that input source A? What is it that actually gets read out? Remember, like I told you, the actual write happens only on the positive edge of cycle number 3. That means the read operation that you are going to do at that point, you will end up reading a old data from that particular register S8. Okay, so what is going to happen here is the instruction that actually goes to this guy will not be S8, it will be some garbage. It will be garbage value, right, or it's some unknown value that we have no idea about. Okay, why? Because what we are actually looking at is this signal here. Okay, what we are looking out here is this RD1E and RD2E. Okay, so what are we looking at? These signals here are basically RD1E and RD2E to the ALU, and they are getting sampled by the flip-flop just before it at the clock edge. So whatever was in S8, register S8, it will just get read out, right, through this thing. Okay, so if you look at for example, if I were allowed to plot the contents of register S8 separately, then you will easily see the point that I am trying to make here. So what I'll do is I will write the value of register S8. Okay, I'm going to draw that here separately. Okay, so this is my contents of S8. Okay, I'm going to draw it between these two lines, right. I do not know what it was in the first cycle. Ironically, though the data is ready for writing back into register S8, the write cannot happen until the clock goes high, and therefore even in this period the contents of S8 are unknown. Okay, and therefore what is now going to happen? The clock edge goes high, the write enabled to the register file is high, so there will be a certain delay that happens, right, and you get the contents of S8 here, which happens to be S4 plus S5. However, in order to perform the read operation, you have sampled that data right at this point. And at that point, what was in S8 was complete garbage value. Okay, and therefore the S8 value that is going into the ALU is going to be an incorrect value, and therefore this particular read immediately after write will not work directly in the pipelined processor. Okay, this requires a certain hardware modification for us to handle appropriately. Okay, now what is the hardware modification? There are multiple ways in which you can do it, but if you go back and you look at this particular block diagram here, you pay attention, close attention to the clock at this point to the register file alone. Every other clock in that is going as clock, but that clock to the register file alone has been bubbled to be clock bar. Okay, so therefore that is something that you have to be careful about, right? You have to note that thing very carefully. So if you put clock to the register file, it's not going to work. Therefore you put a bubble here. Okay, you put a bubble here and then control it with the same clock. Okay, so now what happens? Something very interesting happens. Instead of this whole data getting written, right? So if you look at what is going to happen in this second case, right? When I use clock bar going directly to the register file, okay, and if I look at the contents of S8 here, S8 register, okay, so this is clock cycle 1, 2, 3, okay. So if you look at the contents, now I will also mark in orange here the falling edge, because I am also interested in clock bar, because the falling edge of the clock is where the rising edge of clock bar will be, and therefore the register file alone for write operation, only for the write operation, remember it's only write that is sequential in the register file, is now going to respond to the positive edge of the clock. Therefore my S8 will be junk in my first cycle. Okay, now let's go back and look at what is getting written. Okay, I'm going to take only the signals that are going to the register file in this particular, that happens to be RDE, result E and reg write E. Okay, so let me plot that alone separately here. RDE, okay, result E and reg write E. So obviously these being E signals will be ready only in the second clock cycle, right? It cannot happen earlier than that. Right, so this is going to happen, I think, right after the clock edge. So the RDE will be immediately available. Right, so this is going to be S8. Right, the result E, remember, is going to take some time. Okay, so the result E is going to take some time for you to evaluate S4 plus S5, because you have some huge delay like 120 picoseconds through the ALU, and therefore so this will take some time, right, and this will be S4 plus S5. Okay, the reg write E is again no problem, because the decode happens and then the reg write E will go up immediately, TPCQ after that thing. So reg write E will be 0, assuming it's 0 here, right, and then it just goes up at this point. Okay, now where is the write going to happen? The write is going to happen on the falling edge of the clock, or on the in between the rising edge of second rising edge and the third rising edge, and therefore the point at which data gets written into my register file is here. Okay, so if you look at the contents of S8 now, the register S8, it will be garbage until this point, and then it will basically get reflected with the appropriate data that was in result E. And what is that value? That will be S4 plus S5, right? However, note that if this has to happen correctly, the whole operation needs to be set up before the rising edge of the clock going to the register file, and that is the falling edge of thing. So this entire ALU data memory read plus mux, everything should finish in half a cycle and set up before that. So therefore, if you look at this delay, right, the result E delay here, if you look at this, the result E has to set up at least TRF set up before the falling edge, okay, and that is going to be a problem. It's not going to be that easy for you. And of course, remember that result E itself, so how much time is that going to take? The source A, source B will be available TPCQ after the clock, after the rising edge of the clock, because the rising edge of the clock is still what samples this flip-flop, right? If you remember, this flip-flop here is sampled by the rising edge. So it will take TPCQ for the TRD1E to be ready, then TALU, okay, in fact there is a TMUX before that. So there is a TMUX, TALU, then there is a data memory which can be bypassed, and then one more TMUX. So all this has to come, plus TRF setup has to happen within a half clock cycle if you want this to be a successful operation, right? However, the keeping the timing apart, what we notice is that in order to make this pipelined operation work, because the read also is now sequential, remember, just putting a flip-flop after that combinational register file made the read also in some sense sequential, and which means unless the clock comes, the RD1E, RD2E will not be available, right, will not be available for the ALU to sort of use, right? And for that reason we had to employ the clock bar for the register file to use appropriately, okay? Now, why did we get away with all this in the single cycle processor? We never had this problem in the single cycle processor. Remember, in single cycle processor, the register file still had the clock going to it appropriately. The reason for that is when we had the same two instructions, right, S8, S4, S5, then subtract S, what is it? I don't remember. So this is supposed to be S2, S8, S3, sorry. S3, right? So for that, let's go back and look at this diagram that we had earlier, right? So that we can just sketch that and understand it a little better. Yeah, so let's take this picture for us and then we'll okay. So we come back here. I'm going to put this picture on the side here. Okay. So basically what we had was, in this particular case, right, what we had was, you had every instruction executing in a single cycle. So that was reasonably easy. Clock rising edge, this is my clock, right? So if you look at the INSTR, right, that came out, basically it would simply do this thing here. So this would, the PC would launch it, right, and you would get the instruction add S8, S4, S5, right? Then this would come out in the next cycle as subtract S2, S8, S3, right? And then this would go here. That would be the next instruction, right? And the control block was basically decoding all this, and the reg write signal, you know, if you look at the reg, right, it would go high here. It would take some time for the decoding to finish, and it would just make this signal go high here, right? And of course the subtract also was going to be high, and therefore that would also continue like this, right? And then what happens, if you look at reg write, it is there. Then your ALU result, right? So if you look at my result, so let's just again focus on the signals coming back to the register file. So this is going to be my result, right? And A3 is going to be my destination register, right? So that's coming from the instruction itself. Okay, so that is available right in the beginning. The result is going to go through a register file. It's going to go through that entire critical path, right? So if you look at this, this is going to take its own sweet time, and finally it will settle to the actual value, and this will be S4 plus S5. S4 plus S5, okay? And where my reg write has gone up and the clock is high here, so the result, if you look at the contents of S8 now, the register S8, it will be unknown in this period. We have no idea, right? It will be unknown here because it's some value. After the next clock cycle, it will basically take again some time, and then it will get the actual value, which is S4 plus S5. Okay. Now what is going to happen? The next instruction, which is the subtract, which is using S8 itself, is going to go through the same process. But because this whole thing is combinational in nature, right? The read being combinational in nature, you are not limited by sampling the data at the rising edge of the clock. When S8 changes at this point, which is after the clock, that change will still go through the ALU, will go through the register file to the ALU and start. So if you look at the result here, right, this, you know, once things starts changing at this point, right, this will start wiggling and it will finally settle to its final value, right? So after my S4 plus S5, so earlier what was happening is relative to the clock, right, relative to the clock, this result would be ready earlier because there was no, the register contents S4 and S5 are assumed to have been written already, they are already stable. So the result would appear slightly earlier. But now when S8 actually changes a little later into the clock period, that will still trigger the combinational path through the ALU, through the MUX and all, and it will still, you know, end up giving you the right result of S4 plus S5. Hopefully that is sufficiently set up before the TRF setup so that you can write it back appropriately into the register, right? So this point might move a little to the right here. That's the only change with respect to, it may go really close to the clock edge. So this will start moving to the right, and because of that you can be a little bit tight on the setup time, but if you keep the clock period slightly relaxed, you should be able to handle this appropriately. That is the reason we never saw this problem of read immediately after write in the single cycle processor that we implemented, and this is very particular only to the multi-cycle and the pipelined processor execution, right? So now let's go back and look at the the pipeline processor, the 5-stage pipeline processor that we wanted to continue with, right? So the next, having constructed the 5-stage pipeline processor and also looked at a 2-stage pipeline processor and all that, right? What we want to now do is to jump into the pipeline processor hazards. Okay, and pipeline processor hazards really is very related to the problem that we just discussed. It happens when an instruction depends on the result from an instruction that hasn't completed. Okay, because it takes multiple clock cycles. In the second clock cycle, like we saw now, until you change the hardware of the register file going from clock to clock bar, it was not possible for us to finish use the same hardware exactly for this consistent functionality. So there are two types of hazards. One is a data hazard, where you have register value is not yet written back into the register file, just like we saw now, and a control hazard. A control hazard is when the next instruction has not been decided, for example in a branch instruction. Okay, so what you see in the data hazard, right? I'm showing you here. Basically the maybe I'll take this picture over there, okay, so that we can use it and annotate a little bit, right? So yeah, let's get this over, right? So we are now looking at data hazards, okay. Right, so these are data hazards out here. So it's exactly the same sequence of instructions, except now we are dealing with a 5-stage pipeline and not a 2-stage pipeline. Okay, so therefore the kind of hazards will be slightly different. Okay, so what we are doing here is the S8 register is basically a destination register for the first instruction. It's getting used as a source in 3 other instructions immediately after. Okay, 3 consecutive instructions. So by the way, if you don't modify any hardware, if you don't modify any of this hardware, you just use the single cycle hardware as it is with clock in the register file and all that, then if you want this sequence to work, the only way you can do this is to add no operation in between. Put 3 no operations in between, right? Then the data will get written back, and then you do the next subtract. All this thing will work consistently. Of course, no operation is a pseudo instruction in RISC-V that is going to get implemented as some add immediate x0, x0, 0, right? But in any case, so this is how I basically don't do anything for the next few clock cycles, so that the data that is to be written back to the register is eventually ready, and then you do the read and then continue. Then this will work, but that's a very trivial solution, obviously very inefficient, because you're just idling the processor. Remember, idling the processor is what is going to kill your performance and screw up your program execution time. Okay, anyway, so you come here. What we now want to see is the data hazards that are caused by this S8 being reused in the second, third and the fourth instruction. So the second instruction is very interesting because the write back to the register file happens only in cycle 5 for the first instruction, but in cycle 3 you expect the data to be available, right? So that the register file can read it out and you can give it to the ALU. Okay. Likewise, in the third instruction also, you are expecting the same thing to happen in the 4th clock cycle. And of course, the 4th instruction in the 5th clock cycle, you want exactly this to happen. Okay, that's why you see this particular case. This is exactly what we discussed in the 2-stage pipeline architecture now, which is what we call the read immediately after write problem. And what did we do for that? We said you can use the same register file, make the clock as clock bar, then it will work correctly. Now what does this mean? It means that the write back is happening in the clock cycle half a clock cycle earlier than the respective clock edge, right? That's why you look at this block that we have here, the shading is in the first half of the rectangle. That means writing is happening in the first half, but reading on the other hand, register file read is happening in the second half. So that is basically because we are saying negative half clock bar controlling register file, and read of course is basically, so I think that's the most important part, right? So what we said now, okay, is there are two things. So how did clock bar and clock suddenly come? How did we implement this first half and second half, right? If you look at this, this is the clock, okay, this is my internal clock of the register file which I have inverted. Then I am getting data out and then I am giving this to a flop, but this is controlled by clock. So the data coming out of the register file, okay, out of the register file is going to get controlled by clock. That means the positive edge of the clock, it will come out, right? But clock bar is controlling the register file, which is what matters for the write of the register file, and therefore the negative edge is what is going to control that, and that's why the first half second half concept can be shown in this particular way. So therefore what we are basically saying is, yes, it's the same register file, you are trying to read from write to same register, read from the same register, but they are happening at different times and they are separated by half a clock cycle in this particular implementation, and therefore in this data hazard, read immediately after write, not immediately, read after write is really not a concern, and it is solved by making the clock to clock bar in the register file. However, the other two hazards that we see in cycle 3 and cycle 4, these are not fixable immediately, and therefore you need to find a way to add some more hardware to figure out how this can be overcome.